Okay, guys, actually, this is the system verilog session we are going to discuss. This is the last, not last. We have completed all the topics of the system verilog, like from starting onwards, the data types or different types of arrays, or how to create the mailbox, what is been my mailbox, and all. Right? Oops concepts, coverage concepts, randomization, and constraints concepts, all the things are completed, right? By using all those things, how can we create the test bench using the system verilog? Okay, if you see, for a newly joined person, so if you see, we can write the test bench in the verilog also. But whenever we are writing the test bench in the verilog, what happened, we cannot create the high level test bench, because in the system verilog, because as we are using, any disturbance is getting from my side.
No, ma'am.
Okay. Okay. See, whatever we are taking the complex level, the complex architecture level, right? Whatever we are writing in IP level or SOC level, we cannot use the Verilog HDL. That syntax is wise, or it doesn't support for the new features, higher order features, and it doesn't support for the dynamic nature. Okay, you all know these things. That's why we are moving to the system Verilog. We completed all the things in the system verilog, right? What are the main useful concepts to write the architecture, right? So today we'll see how to write the system verilog whole test bench. We already seen how to write the whole test bench in the starting demo session only, right? So we'll see for particular example how to create the system verilog test bench. Okay, so can you tell girls what are the different blocks we have to write the test bench?
Generator, driver, monitor, and scoreboard, ma'am.
Generator, driver, monitor, scoreboard. Okay, what is the use of this? How can we connect driver to the generator to the driver?
By
Generator,
transact
driver, monitor, scoreboard, by using the transactor. Okay, how can we transfer the data of generator to the driver? Okay, how can we connect this test bench to the DUT?
by interface, ma'am.
By using the interface, by using the virtual interface. Can you tell me why we will use virtual interface instead of interface?
Because virtual means and pointer, ma'am. We use here to point and uh, functionality, ma'am.
Okay, interface is nothing but whatever we have used in the Verilog, that is a normal interface. But virtual interface supports dynamic in nature, because as we are using all our classes, generator is a class, driver is a class, everything class based verification, nothing but dynamic in nature. To support those class based verification, we are using the virtual interface, right? So the top module is environment, then test bench. We'll discuss clearly now how to write the test bench architecture. Okay. See here, this is the system Verilog test bench architecture. But when we are writing the Verilog test bench, we don't follow any architecture. Just the test bench flow we will follow. Just writing the, creating the module, initializing the reg and wire signals, and initiating the DUT, and taking the input signals, input variables. Like that, we will write the Verilog program simply. But in system Verilog, we have to follow the architecture. Okay, so this is the architecture we will follow to write any type of test bench, whether it is a combinational logic circuit, or whether it is a sequential or finite state mission, or it is a memory, whatever we will find, we will follow this same architecture to write the program. Okay, so UVM also same. System Verilog and UVM both follow same architecture, but in UVM we will have different type of only this block will be different. There will be, it will be sequencer which generates the variable, but here we'll use the generator. That is only the difference. Remaining all are same. Okay, so generator is nothing but it generates the randomized variables. Whatever the randomized variables we are using in the generator, it generates the randomized variables, input variables. Okay, those values, suppose in Verilog how we will assigning some values to the variable by within the initial begin, a equal to 10, b equal to 20, c equal to 15, or d equal to something, or address equal to something, data equal to something, like that, right? But as we are using randomized random constraint based verification, within the generator it automatically randomize the values, okay, by using the randomized method. Whatever the randomized values are there within the generator, we will send those values to the driver. Okay, driver is a class, generator also a class. Okay, by using the driver we can send those randomized values to the DUT. Okay, in Verilog how we will send the data to the DUT, the input values whatever we are writing will connect with the DUT here. To the DUT we will connect our design, right? Like that, here there is a driver block to generate to transmit the generated values to the DUT. Okay, so how it is transmitting to the DUT? Through the interface. Okay, through the interface is nothing but it will work like a mediator between the test bench top module and the DUT. Okay, so here interface is a static in nature, that's why we are moving to the virtual interface. This interface is nothing but whatever we have written in the Verilog normal interface. Okay, so that's why we are moving to the virtual interface. Okay, and when we are sending generator to driver, in middle we will have one box, one block. Okay, that is nothing but mailbox. Mailbox is a communicator between the generator and the driver. We cannot send directly data to the driver. We will use the mediator, communicator between generator to driver. Okay, for more synchronization purpose. And whatever the DUT we are sending the data, DUT will do the operation according to its functionality. It will do the functionality and it should generate the output, right? So that output it will send to the monitor. Okay, that output it will be sent to the monitor. So what is the need of monitor? The data will be taken from the DUT. The monitor will send to the scoreboard. Scoreboard is nothing but whatever we are returning in our transcript. Okay, so scoreboard is used to check our output. Suppose this output is getting for us. Okay, this output we need to check whether it is correct or not. How we will check that output whether it is correct or not? If you see in your BTech, when you are doing BTech, we'll have labs, laboratory, right? Different labs will have. How you will check your how you will check your practical calculations? You will check with the theoretical calculations, right? Like that, in scoreboard we will generate the logic, which is a golden reference value like your theoretical calculations. Okay, in scoreboard we will generate that logic to check the whether output is correct or not, just like a reference. Okay, with these reference values we will check our original output. If both are same, then our output is correct. Okay, that thing we will check in the scoreboard. Okay, so these three combinedly call as a agent, these four combinedly call as a environment, just one top module. Okay, environment is nothing but combinedly these four, just like a top module. Okay, this environment connection is the test is one of the top module to this environment. Okay, for this test whatever we are connecting with our DUT, both for both the top module is test bench top. Okay, this test overall test we are connecting with our DUT interface, right? So that is nothing but test top module. Okay, so whatever you have seen, the generator is a class, transaction is a class. In the transaction we will have all inputs and outputs. Okay, the driver is a class, monitor is a class, scoreboard is a class, everything class. Okay, so whenever we are writing the test bench, this is how we need to follow the architecture. Did everyone understood? Have any doubts? Have any doubts? Did everyone understood?
Yes, ma'am.
Okay. What about new students? Have you understood everyone? No doubts? Okay. So we'll see one program how to write the test bench practically. Okay. We can write different programs. We can use a combinational logic circuit or a sequential logic circuit, any flip-flop or any adders like that we can take. But in this session, I am taking on FIFO. Okay. Asynchronous FIFO. You already know how what is the use of FIFO, right? What is the FIFO? It is a memory which is used to store the data. Okay, so FIFO has a n bit data. It has a write pointer and a read pointer. FIFO is nothing but first in first out. We will store the data within the locations, right? Whatever we are given first, we will take those output as a first, like input. Here we have given first 1 2 3 4 5 6. Again we'll take from input output from first location, second location, third location, like that. By using the pointer, we will point to the right pointer and read pointer will be there. Okay, suppose first right pointer is in 0 location, means we need to count plus 1, right pointer plus plus, so it will go to 1 location. We'll store some data in the first location. Again it will go to the second location, right pointer plus plus. That means count is incrementing. So we'll store in this third location some data. Again it will go to fourth location. Again it will go to fifth location. Like that, by using the right pointer, we are storing the data into the FIFO. Okay. So in FIFO mainly we have two signals, empty, full. Okay. If empty means what? No data in that particular FIFO. Okay, when it is empty we can store any data. Okay, once it is full we cannot store any data, right? So to know whether our FIFO is empty or full, we are checking with these conditions, empty or full. If it is empty, we cannot read the data. If it is full, we cannot write the data. Okay, those things we will check with the empty and full conditions. Did you understood the FIFO simply? So when we are reading the data by using the read pointer, so read pointer will start from the zeroth location. A read pointer at zeroth location, the data will be read outside. Again plus plus, it will go to first location, data will be read. Again plus plus, count will be incremented. Second location, the data will be read. Third location, the data will be read. Like that, FIFO we will do the write operation and read operation in that way. Okay, did you understood everyone the FIFO? So now we'll see how to write the program for the FIFO. Okay, see here first, tick define. Tick define is nothing but which can be defined globally. Okay, so like a parameter. Okay, so tick define width. We are declaring the width as a 3 size, and tick define buffer size 1 must be less than buffer width. That means always it should be less than 3. It is not less than, it is shifting operation of 3. Okay, and module FIFO, what are the signals should have in the FIFO? Clock, reset, data input, data output, write, read, empty, full, FIFO counter, read pointer, write pointer, as whatever I have explained before, right? So what are the inputs? Single bit inputs. Reset is the single bit, clock is the single bit, write, read, these are the single bit. Okay, data is the 8-bit input, data out is the 8-bit output, and empty, full also output, because we are checking the conditions empty and full. Okay, that is also output. And FIFO counter, what is the FIFO counter? What is the bus width here? 3. Okay, that macro we have used here, 3 down to 0. 3 down to 0 means it's a 4-bit counter. Okay, it's a 4-bit counter. Next, we have taken some register variables, that mean temporary variables to store the data temporarily. Okay, then we can first we are storing the data temporarily, then we are moving the data to the permanent output. Okay, so here reach 7 down to 0, data out is the temporary register, and empty equal to 1, full equal to 0, these also temporary variables. Okay, not actual outputs. And range macro, by using the macro, bus width is nothing but 3 down to 0. FIFO counter we have taken, output range, read pointer equal to initializing, that means FIFO always first in first out, right? So you should not start from last, suppose seventh bit location, you should not start from the seventh location or from middle of the location. Always first in first out means it should start from zeroth location, and reading also from zeroth location only. That's why read pointer equal to 0, write pointer equal to 0. Okay, next, memory, we should declare the memory also. One memory is needed for FIFO, right? So buff memory, buffer size, whatever the size, minus 1 down to 0. Okay, so for the conditions, for empty condition and full condition, what we are writing, always at the rate of FIFO counter, based on the FIFO counter, empty equal to full counter equal to 0. Okay, that means FIFO counter equal to 0 means what? That is empty. Okay, the overall FIFO is the empty. Full means FIFO counter equal to buffer size, whatever the size we have taken. If FIFO count value is equal to size means what? Almost all the locations completed, count reached to the maximum value, that means FIFO is full. Okay, so those are the empty and full condition. Not only like this, you can write in your own way. Okay, if you have some other logic, you can write in that logic by using that. Okay, next, coming to the FIFO logic, always at the rate of passage clock or passage reset, uh, begin. If reset is high, FIFO counter is equal to 0. Okay, else if full is not high, and right is high, if right is high and empty is not high and read is high, then what happened? FIFO counter equal to FIFO counter, that means we are initializing the counter value. First of all, we are updating the counter value when both the FIFO and empty is not high. Okay, and else if full is high, right is high, we can perform only write and read operation different times. We already know, we have seen in the protocol also, right? Write and read operation cannot be performed at a time. One at some time write operation completed means then only we can go for read operation. Both write and read operation cannot perform at a time. We already know that thing, right? So here full is not high. Full is not high means what? It is empty. Empty means we can write the data into our memory. Okay, so it is writing FIFO counter, counter plus 1. We are incrementing a counter size when we are doing the write operation, right? And if empty is not high, that means it is not empty. Whenever it is not empty, we can do the read operation. We can do the read operation according to your final state mission, like that. Here we are not giving what is the output and what is the next state. Here we are writing only the functionality, just not writing the output. Okay, in next always block we are writing the output also. So here count should decrease the value whenever doing the read operation, the count should decrease the value. Okay, because it is checking for empty. The read means the empty should high, full should high, it should get to empty. That's why. Else FIFO counter equal to FIFO counter, same value. FIFO will counter value will get the counter value. Next, always at the rate of passage clock or passage reset. If reset is high, data output equal to 0, and if read is high and empty is low, that means it is not empty. Read is high, that means it is full. We can read the data. See, Data out equal to buff of memory read pointer. Right, read pointer is nothing but maybe the pointer is here, the pointer is here, here. Anyway, we are writing the data. You know how to read and write the memory. Suppose this is the memory location. Location 0, location 1, location 2, location 3, location 4. Okay, I want to write 50, value 50 into the third location. So how I will write value 50 into third location? Suppose I am taking the memory name as MEM. Okay, MEM of third location is equal to data input. I am taking a value, or you can put as a data input. So this is the memory, the mem of 3, third location. The 50 will be sent and stored into the third location. Okay, same I want to read this data. How can I read the data? Data output, data out equal to mem of third location, mem of 3, or you can put here as a write pointer or a read pointer, like that. Okay, so this whatever the data is there in mem of 3, the data will be stored in the data out. Did you understood? Stored into the data out. For any memory, whatever the memory you want to write, you want to develop, you need to follow these two steps for reading and writing operation. Any memory, whatever the DRAM or SRAM or the dual port RAM or normal RAM, ROM, FIFO, LIFO, whatever, you need to follow these two. Okay. So same thing we have reading the data here. Okay, else data out equal to data out. Always at the next, always at the rate of passage clock. If right and not full, it is not full. If it is not full means, if it is not full means we can write the data. Right. So it is not full. It is empty. It is empty means we can write the data. So buff of memory write pointer equal to data input. Did you understood that particular memory of write pointer, particular pointer we are writing the data. Okay, particular location. Else buff of write pointer is equal to buff of write pointer. Did you understood here what is the meaning? If this condition satisfied, then only we are writing the data into this particular memory. Otherwise, that particular location value we are writing into that location only. Okay, no change operation, nothing but. Next, last, always at the rate of passage clock or passage reset. If reset is high, begin write pointer equal to 0, read pointer equal to 0 in reset condition. If full and right is high, if full is 0 and right is high, means right pointer should be +1. Right, full is not high means it is empty. It is empty means we need to write the data into all the locations. Okay, if empty is 0 and read is high, it is not, it is empty, it is not empty, it is full. It is full means the right pointer is starting from the 0 location. Again it is go to +1, +1. Maybe you will get doubt why we are doing for both +1, +1. Right operation +1 means read operation should do -1, right, like increment and decrement. No, as we are using the FIFO, as I said, first in, first out. Writing also first input, reading also first output. So both are +1. Both will start, the pointer will start from 0th location. Okay. So did you understood the code, everyone? Design code? Design code, everyone understood? Maybe it's somewhat like if you don't understand, I will share the code, right? So you can go through that and you can understand.
Ma'am, why you have preferred for active low region, ma'am?
Active low region here. That designer issue, like we can use active low signal or active high signal. here active low in the sense it is not a active low. Just we are telling here FIFO is a 0. Simply the coding style is a simply simple way. If you want to write in a different like complex way, what you need to do, if full equal to 0 and right equal to 1, like this you need to write, right? See how much complex it has. But if you take not full means it is 0, here right means automatically it is 1. The difference is there, right? That's why. Okay, have any doubts? Can we see the test bench how to write for this program? If you see Verilog, how you will write? You will just instantiate this DUT and you will write the inputs it in the initial block and you will generate the clock, right? But when we are writing in the system Verilog, it is different. Okay, if you don't have any doubts in the design, we will move to the system Verilog test bench. Okay, no doubts? Okay, see here how to write the test bench. We'll start with the interface. Okay, first interface, how to write the interface. Okay, see, interface, name of the interface is FIFO I, and input logic clock reset. Okay, we are just within the interface we are writing the clock reset because the synchronization things we need to write here. Okay, and logic all the inputs, inputs outputs everything, logic read write reset full empty data out data in read pointer write pointer FIFO counter. Can you tell me why we have used the logic here? We already discussed. Can you tell me why we are using logic?
Logic is an unsigned data type.
Okay, mainly what is the need of logic? In Verilog, what we have written here for declaring inputs and outputs?
Fire, ma'am.
Via and reg data type, right? So logic is used to declare both, as we are using wire and reg data type when we are doing the initialization or when we are doing the inputs declaration and all, it is getting a mismatch race conditions and all, right? That's why a logic is the data type, new data type created in the system Verilog. So by using the logic we can write either reg data type or write wire data type. No need to mention particularly reg or a wire. Both in place of both we are putting as a logic. Okay, to avoid the confusion. And the clocking blocker, we discussed the clocking blocker. Suppose when we are writing the when we are connecting the driver to the monitor, suppose here driver to the DUT and DUT is connecting to the monitor, driver to monitor, sorry, driver to DUT, monitor to DUT, the synchronization should happen, right? That's why we are using the clocking blocks. Clocking driver at the rate of passage clock, input reset, output. Here these are the outputs to the driver. You need to check those things, data in write read, these are the outputs to the driver and these are inputs to the driver. You already discussed those things. And clocking block, monitor, passage clock, input, these all are inputs to the monitor. Why all inputs to the monitor? because all are coming from the DUT only. All the signals are coming to the DUT. So these all signals are input to the monitor. Okay. So as we are data in is the output to the driver, because these inputs, whatever the generator driving the inputs, those are sending driver to the DUT, right? That's why output to the driver. And mode ports. Mode port is nothing but when we are connecting all the ports for more synchronization purpose, we'll use the mode port, right? DM clocking driver. Whatever the driver clocking is there, same we are putting here. If you put same, what happen? No need to write all these things again. Directly we are putting clocking driver here. Okay, input clock comma reset. Those things, and clocking monitor input clock comma reset. So these are the interface. You can avoid the clocking block mode port also. This is not mandatory. We can avoid the clocking block and mode port also. When you are writing initially, you just avoid those things and you can write, no problem. Okay, when you are practicing more examples, when you are in like you know the coding well, then you can use these things. Okay, and coming to the transaction, where we are using the transaction between the generator to the driver, or monitor to the scoreboard. Generator to driver, monitor to scoreboard, we are using the transaction. Within the transaction only we will have the all the inputs, whatever to be randomized, whatever to be randomized. Those things you need to remember. Interface is nothing but interfacing the DUT with a design. Transaction is nothing but the generator, whatever we are using the randomization, those things, whatever the variables we are returning in the transaction, those variables will be doing the randomization in the generator. Okay, so what variables will do the randomization? Only input variables will do the randomization. Output variables need not to do any randomization. Output means it should get the output from the input functionality, right? That's why we need to do the randomization for the inputs. Okay, see, class transaction is the class name. Okay, name you can take either it is a trans or transaction class or trans class, like that, whatever user defined. So if you say write, read is the input, data in is the input. So these are three are the inputs. Here reset also input, but it is not doing the randomization. I think somewhere we initialize it with the default value. No need to do randomization. Okay, see here, write and read out the bit data type rand c. Why we are using the rand c? Because when we are doing the randomized method, when we are using the randomized method, only the input should randomize. To know the difference, suppose here in the generator block, if you see here, um, if you see here 25th line, tr dot randomize. Tr dot randomize means whatever the variables is there in the tr transaction class, all the variables it will be randomized. All the variables it will be randomized. But is it necessary to randomize all the variables? Is it necessary to randomize all the variables?
No need, ma'am.
No need, right? That's why for only inputs we are mentioning as a rand. When wherever we mention as a rand, only for the inputs, only those variables will do the randomization. Okay, so that is the rand. Can you please join for the next session with the same link? With the same link, can you please join for the next session? Okay, so you understood why we use the rand, right? So whatever the input variables are there, for those we need to write the rand. Okay, if you don't write rand, it won't do the randomization. Okay, so inputs must declare with a rand, outputs no need to declare with a rand. Its data type is enough. Okay, so constraint. See here, constraint. we do the constraints, right? To do the randomization, to make we can use the constraint. Okay, to make, to use the particular value. So what are the constraints we have written here? Write, read, enable. What is the write, read, enable? It is a sorry, it is a constraint name. Okay, tes is the string name for doing the write operation. Okay, what we are telling, write equal to 1, read should generate 0. When write is generating 1, read must always 0, because write and read operation should not perform at a time. Okay, and test read operation, read is equal to 1, write should get 0. See how we are writing the write. If you don't write these constants, what happen? When write equal to 1, read also may generate 1. When read equal to 1, write also may generate 1. Right? That's why for controlling the those values, we are doing the constraints here. Okay, write equal to 1, read equal to 0, read equal to 1, write equal to 0. Like that, class trans2 extends trans here. Again, this one extending here. These are the two classes we have written in the transaction class. When write and read is not equal to 0, data in must be less than 10. Data in less than 10. Okay, that means it should randomize between 0 to 10. Actually, what is the data input here? 7 down to 0. It is a 8-bit data, but we are telling it should be less than 10. Okay, so that is the transaction class. In transaction class, we need to write mainly declaring the random variables. Okay, next, generator. What is the generator? We will randomize the values in the generator, right? So here if you see, class gen is the generator class name. All these things whatever we have seen here, randomization, constraints, coverage, interfaces, these things all we have discussed starting only conceptual wise we discuss. So if any new students join, maybe somewhat confusion, but I'm trying to tell clearly the conceptual wise also. So see, class generator transaction, we have created the instance. Okay, if you see in YouTube I have posted what is meant by instance, what is meant by object, what is meant by class. You can go through that. So trans instance is very important to access the variables. And trans one also we have created instance. Trans 2, static int count equal to 8, initializing the count value with 8. We have created the mailbox. Why the mailbox? When we are transmitting generator to driver, the mailbox will work as a communicator between them, right? That's why G2D, generator to driver mailbox, has created. Okay, this is the constructor function new. This dot G2D equal to this dot G2D, because we are accessing within the class. That's why we have used the this. Otherwise, we have to use the object. Display allocated memory. Whatever the allocated memory is there here, for the FIFO, we have displayed that allocating memory. And task main int I, display count, repeat the count value, whatever the count value we have taken. Tr equal to new of. What is the tr? Tr is the instantiation of the transaction class. Trans, for trans, we created tr. Tr is the instantiation. Tr equal to new of, creating that tr. Tr dot tes equal to write. This tes is the string of here. String tes. The tes is write. When we are doing this write there, directly it will come to here. Okay. So it will write the string and displaying the generator writing transaction. Next, if tr is not randomized, tr is not randomized means it should display not randomized. Otherwise, whatever the randomized values are there, it should generate those values g2d dot put off. What is the put off? Put off is nothing but whenever the generator class is there here, generator driver between monitor. monitor, to the monitor we need to send the data, randomized data to the monitor. Right here the values, input values will get randomized. This data will send to the mailbox. So we are using the put method. Put G2D is the name of the mailbox. Dot put of tr. What is the tr? Whatever the randomized values are there here. Okay, put dot tr, put of tr. Those all the variables will be putted into the mailbox. Okay, so displaying all the variables here. Tr dot data in, tr dot read, write. Okay, so whatever you want to access the variables, you need to access through the object. Tr is the object here, right? And I plus plus at the rate of FIFO I driver, we are calling that thing. And run method. Int j, repeat count for the second transaction. This is for second T2 of trans. T2 equal to new, T2 equal to T2, Tr equal to T2, Tr that means rand 1. We are calling this rand 1. Okay, accessing that rand 1. And Tr dot random is fatal. Dollar fatal is the assertion. Okay, dollar fatal, dollar error, dollar info, dollar warning, these are the assertions. Okay, randomization failed. If dollar fatal, it is a randomization failed. Okay, otherwise G2D dot put of T2. Okay, here we have written three types of transaction, but no need to write the three type of transactions. One single transaction is enough actually. But here we have taken three type of constraints. One constraint within the trans class, second constraint is in trans 1, third constraint is in trans 2. If you observe the inheritance concept here, here we didn't declare what is the read, what is the write, what is the tes and all. But as we are using the inheritance, trans 1 should extends from trans, it can be used all these variables. Okay, that is the inheritance concept. By using the three transactions in the generator, we are doing three times. Okay, sending the data to the mailbox. Okay, next driver. Don't think like it is very difficult. It's very easy. All the things are same, but only T2 we change, only T2. Okay, driver. What is the driver? What we need to take in driver, there will be interface and DUT. Okay, that means the mailbox is connected to driver. That means mailbox we need to create. The driver will be connected to the interface. That means interface we need to create, not interface, virtual interface. These things we need to create for the driver class, right? So class driver, virtual FIFO I, B FIFO. What is that FIFO I? If you see here, what is that FIFO I? It is the name of the interface. For this interface name, we are telling virtual. Virtual VFIFO. VFIFO is the name of the virtual interface of this particular interface. Okay. Int count and functional new constructor FIFO and mailbox. These are those things. Reset, we are doing the reset operation, initialization operation. Okay, dollar display, enter into reset, vfifo dot reset. Okay, these things we'll discuss tomorrow. Okay, driver monitor and remaining things we'll discuss tomorrow. It will anyway, it will take 2 classes. So many things are there. Okay, shall we discuss tomorrow remaining part? Hello.
No doubt, ma'am.
Okay. Okay then. Thank you. I will share this FIFO code. Try to implement this FIFO code using Verilog. Okay. Try to write using Verilog first. If you get the output, then you can try with the system Verilog. Okay, thank you. Everyone clear up to transaction class?
Yes, ma'am.
Okay, so today we'll discuss the remaining blocks, generator, driver, monitor, like that. So coming to the generator, in the generator, yesterday only we have discussed the generator also, right? I think so. We'll discuss driver today. So driver, if you see driver, what are there in the driver, the mailbox, whatever the generator mailbox is there, put method, by using the put method we have sent data to the mailbox, right? So the data should transmit it to the driver. From this driver we need to transmit to the DUT via interface. Okay, via interface means here already we have created the interface. We cannot transmit through the interface, we have to use the virtual interface, right? So those things we will see here. Okay, so class, driver, virtual. What is the instance of interface? P for I. P for I is the instance of interface. Virtual interface is nothing but instance is v FIFO. Okay, v FIFO is the instance of virtual interface. Next we have created the mailbox G to D, already created in the generator. Int count value, this is the constructor. Function new, within the constructor what we have written, virtual interface which is connected to driver to the DUT, and mailbox. Okay, these two things we need to use as a members here for the function. Okay, this dot v FIFO equal to v FIFO. Why we are using this dot when we are telling the this concept we already discussed, right? So whenever you are accessing within the class these variables, we need to use the this. Outside the class means we need to access through the object. So this dot v FIFO equal to v FIFO. This dot G2D equal to G2D. End function. Now reset. First task is a reset. Whenever we are doing some functionality, first we need to do the reset operation, right? So dollar display entered into the reset. What are the things we need to reset? All the inputs we need to do reset. If all inputs are reset, automatically output will get to reset state, right? So at the rate of v FIFO dot driver I dot RST. What is the driver I here? The class instance. Okay, sorry, driver I is nothing but the name of the within the here. If you see clocking block, and here mode port, driver I is nothing but clocking block name. Okay, so we are accessing the clocking block name with respect to this clock. It is telling with respect to this clocking block driver I. Okay, so actually we will write at the rate of posage clock, at the rate of negage clock reset, like that normal small circuits, but with respect to the clocking block here, right, we have considered. So that's why v FIFO dot driver I dot reset. Okay, at this time what we need to do, v FIFO dot, what is the DM here? Mode port. We are accessing that particular ports, mode port. Through the mode port we are accessing this data in. Data in is declared in the mode port, as we are taking here clocking driver I in this 39 line. If you see interface, all the clocking driver I is nothing but all this data will be declared here automatically, and clock reset. So we are accessing the input, which input, whatever is there in the interface, whatever we have declared in the mode port, how we are accessing that one? Through the virtual interface v FIFO dot DM dot driver I clocking block dot data in. That data in we are accessing through this part. Okay, so equal to 0 we are sending, equal to 0, like that we are accessing read write, like that v FIFO dot DM dot d driver I dot RD equal to 0, like that same write equal to 0, all are making 0. And at the rate of vfifo dot driver I dot reset. That means next clock edge, next clock. Okay. Dollar display leaving from reset mode. That means reset is completed at this particular cycle. Uh, we did the reset, and next cycle we reset is completed. Okay. So entering into the task main. Okay, main task. What is there in main task? Enter into the transaction mode. Okay, forever begin transaction trans tr. Tr is the instance of the transaction. G2D dot get off tr. What is that get off tr? Can anyone? Already we have used here generator is there. Already by using the put method, put of tr, put of tr, we have transmitted the randomized data into the mailbox. Okay, so again we need to send same data to the driver, right? So by using get method, get of tr. Okay, see, g2d is the mailbox dot get of tr. Okay, so driver is getting the data from the mailbox, which is generator put it the data into the mailbox. Okay, so dollar display driver transaction number. Okay, here transaction number. Next, driver getting the values, d input values, write enable value, and whatever you want to display, reader, write, data input, data output, address, whatever the data you want to return in the description script file, you can write all the data, same as verilog display statement. Next, at the rate of vfifo.driver, that means vfifo the driver I means this next clocking block. What we are telling, vfifo dot dm dot d driver right. What we are sending to the right? Can you tell me what we are sending to the right? Nothing but tr dot wr. What is that? What is this vfifo dm dot driver dot I? Is nothing but dut, is nothing but DUT. These things all mode ports. Mode ports are nothing but we are accessing DUT, driver to the DUT, right? So through this interface, see, through this interface, we are accessing particular ports. So to send to the DUT. Okay, so this is the driver block. This is the interface. This is the DUT. The DUT signals, whatever write, read, address, or whatever the signals are there, we are accessing in this path. Okay, so we are sending write equal to tr dot write. Tr dot write is nothing but whatever we have randomized the data in the transaction class. Okay, and tr dot read, tr dot data in, all these things we are sending to the dut variables. These all are left side, all are dut variables, right side all are test bench variables. Okay, like that we are sending data to the dut. Okay, design. And dollar display, whatever you want to write the data you can write here. Next, count plus plus. For every value you'll do the count plus plus, number of transactions. Okay, so dollar display number of transaction. This is the driver. Did you understood driver? What the driver did here? Accessing the data from the mailbox, it got the data from the mailbox, and whatever the data it got from the mailbox sent to the dut. Okay, you got the clarity. DUT not only like this, you can write in a different ways. Okay, here you can mention in the driver like this tick define. Here in design we have used the tick define, right? Like that tick define and path. You can create the path directly here. Interface signals, how to create, how to access the interface signals. That path you can create directly there. I will show you. Okay, see here, suppose this is some other example. See here, tick define driver if, that is the name, how we are accessing cal if is the name of the interface dot driver cb. Okay, driver cb is nothing but whatever we have written in the here driver cb is the clocking block name. Okay, so whatever the signals we are mentioning here, output inputs, we are accessing through the through this path directly. You can define here that ports block. Okay, this driver is the name of the monitor, sorry, mode port. Okay, see, driver is the name of the mode port here. Driver cb is the name of the clocking block of the driver. Okay, same path we mentioned here, whatever we written here. If you observe vfifo.dm.driver I dot some particular variable, same we have defined it a macro. Okay, whenever you want to use a whole hierarchy, you just want to use a d or iv if. Okay, see here, see here, read request command in is the one input, tag in is the another input, data in is the another input. How we are doing resetting, that means how we are sending the data to all those variables through the tick driv if, by using that macro, the macro path already we define here. Okay, so this is another model you can write. See here how we are accessing request one, data in, command in, tag in, all through this macro. Okay, so these are the different ways you can write the program. Okay, did you understood everyone? Did you understood everyone?
Yes, ma'am.
Okay. Next after driver is receiver. Receiver is nothing but monitor. Okay. From the DUT, after doing the operation, we will receive the data, input and output data from the DUT, right? So we can calling also as a receiver. Okay. So class receiver, virtual FIFO I. We are creating virtual interface vFIFO, and we are creating another mailbox that is receiver to scoreboard, or you can call as a monitor to scoreboard. In middle we should have the mailbox, right? So here we use the put method when we are sending monitor to mailbox, and again mailbox to scoreboard means get method. Okay, so here we have created one mailbox r2s, and in count gen g, generator, for generator we have created g, and function we have to create here virtual interface and a mailbox too. And this is the constructor you already know. task Task start int count gen g is the object here. Display receiver module. For transaction class we have created one tr object, and here creating the tr object. So how we are accessing here at the passage of vfifo.mm.clock, that means whatever the clock is there in the mode port here, mm is the monitor. Okay, monitor mode port, or if you want to use the clocking block, you have to use the monitor I. Before, for driver, what we have used vfifo dm. Dm is nothing but mode port of driver. Dot a driver I is nothing but a clocking block of driver. So whenever you are using the receiver, we need to use the mode port mm clock, monitor clock. And if you see tr dot write, what is the tr dot write? The test bench side transaction, the test bench side. What is this vfifo mm monitor wr? These all are coming from the dut path. Okay, so this write data is sending to the tr dot write, because whatever the operation completed, after completing the operation, those data is sending to the transaction class. Why we are sending to the transaction class? If you see in the test bench architecture, when we are sending to the monitor to scoreboard, here via transaction class only we will send. And again from generator to driver, when you are sending through the transaction class, because all the variables are declared in the transaction class, right? So through the transaction only we will send the data. So whatever the data here DUT generated, sending to the monitor, and monitor sending to the scoreboard via transaction. Okay. So write, read, data input, write pointer, read pointer, all the things are sent to the transaction class at the rate of first clock. Next, at the rate of negate clock v FIFO.mm.clock fork. We are using fork join here. You know fork join, right? So transaction tr temporary, just a temporary object. Tr temp equal to tr, whatever we have generated here tr, we are storing those things into the temporary variable. And next positive edge of the clock, tr dot full equal to full value we got, empty value also we got, data out also we got. Why all the inputs is getting in first cycle and all the inputs is getting second clock cycle means, because those are the inputs and these are the outputs, right? Just for a difference, we are taking at the first clock cycle and second clock cycle, just that is the difference. Okay. And dollar display monitor, we are writing all the variables, whatever the values you want, like a write, read, data out, data in, full, empty, read pointer, write pointer, all the things is displaying here. Next, if you see R to S dot put off TR. What is that put off? That means mailbox data we are putting into the monitor data we are putting into the mailbox. Okay. And join none if count equal to 2 into G dot count. What is the G dot count? Whatever the G we have created for the generator. See here, for gen class, here we have created the uh, what is we call object, right? So for that object, what we are telling, count must be equal to 2 into G dot count. That means suppose, or otherwise you can take as equal to directly. Suppose if you are taking the count value of G is a 10. Okay, that means 10 number of transactions you are doing. When you are doing 10 number of transactions at the input side, output side also it must do 10 number of transactions, right? If you do 10 number of transactions here, if output do 5 number of transactions, that means if we get only 5 number of transactions, there is no use, right? So these two transactions must be equal. That means how much time, suppose from the generator you are sending the data to the DUT 10 number of times, that means it performing the operation 10 number of times. But when you are doing in the monitor, when you are taking in the monitor, we should take 10 number of times only. Okay, if you not take 10 number of times, only 5 number of times, means what is the use? Okay, we will miss the functionality for remaining 5 transactions, right? So number of transactions must be equal. Okay, so here number of transactions must be equal, otherwise you can put some more 2 into count also. Okay, but we need not to keep less. Okay, and begin hash 300 finish count plus plus. Okay, this is how we will write the monitor. Did you understood monitor? In monitor what we did, just we did whatever we generated the data in the DUT we took into our transaction class, and through the transaction class we are sending into the mailbox. Okay, whatever we have sent to the mailbox, the scoreboard have to get the data into the scoreboard, right? So what we have to do here in the scoreboard class, scoreboard, mailbox we have created, transaction class we have created, and we have to create one memory here. What I said yesterday, scoreboard is used to check your output value with a reference value, like a theoretical and practical calculations, whatever we did in our labs, right? Scoreboard is used to generate the golden reference values. With respect to that reference value, we can check the output, whatever we got that output, whether it is correct or not. So how can we generate the golden reference value here? Nothing but by writing the expression. Suppose our FIFO is doing some functionality, right? According to that functionality, we will write some program to satisfy some conditions in our scoreboard. If condition satisfy, automatically the output will get. Once the reference value generated, we'll check that output to the main output. Okay, so that is the scoreboard logic. If you see here, function new mailbox, here we have created only the mailbox. Why we didn't created any interface or virtual interface like that? Because scoreboard is not connecting to the virtual interface, it is connecting only to the mailbox, right? That's why this dot r2s equal to r2s. Are you understanding what I am telling, or is it any confusion? Everyone, hello.
Ma'am, can you explain scoreboard once more?
Okay, so what is mean by scoreboard? Yesterday, what we told about the scoreboard, see, we can generate the golden reference value. Suppose our output we have to check with the theoretical. Suppose in your laboratory, if you see whatever the lab you have, whatever the practical calculations you got, every practical calculations to check whether those are correct or not, we will check with our theoretical calculations, right? How we are getting these theoretical calculations? We already know the formulas, everything regarding to that functionality. We will have everything formula and all. By using those formulas, by doing the theory calculations, we will get some value, and that value will be checked to the whatever the practical in kit, whatever we have generated, we will check like that, right? Same thing, the theoretical calculations is nothing but here we are writing some code. That code in the sense expressions which should satisfy our functionality, which should generate some reference value, golden reference value. Okay, so that is the main thing. Scoreboard is used to use it to display the data, and also use it to generate the reference value to check with the output. Okay, so whatever we have, what is there in the run task, r2s dot get of tr. What is that r2s? R2s is the mailbox from where it is getting. The scoreboard is getting from the mailbox. Here we are using the get method. From the monitor we have used the put method. By using the put method we have sent the data to the mailbox, and by using the get method we are sending this data of mailbox to the scoreboard, right? What are the conditions we are writing here? If tr.rd, tr.rd is nothing but the read signal. If buff mem of tr dot read pointer is not equal to tr dot data out. What is that? Can you tell me? Buff memory. Suppose, what is the buff memory here? This is the buff memory, is the name of the memory. Okay, where is the read pointer? Suppose wherever buff memory is nothing but where some memory, this is the memory, these are the locations. Okay, so read pointer, somewhere we have the read pointer. Okay, it should not equal to tr dot data out. What is the data out? Data out is different. Okay, bus mem of tr dot read pointer. Okay, suppose the read pointer is somewhere here location. Here suppose we have the data as a 5. It should not equal to tr dot data out. See, if it is not equal means what it is generating? It is generating error. Okay, actually it should equal whatever buff mem of read pointer, whatever the read pointer is there here, that data must be equal to our data out, right? Output and this read pointer data should be equal. But here we are telling not equal. If it is not equal means it should generate the error. That means the expected value and the actual value are not same. It should generate the error. Otherwise, it should display the both are same. Expected and the actual value both are same. Okay. Else, if tr.w or right pointer, buff mem tr.right pointer is equal to input. Nothing but right pointer is nothing but the data input data we are sending to the particular memory. Okay. Number of transactions plus plus count plus plus we are doing. Did you understood the scoreboard logic? Simple logic. Okay, you need to write very simply. Did you understood?
Yes, ma'am.
Okay. Next, after the scoreboard, what is the main environment for generator, driver, monitor, scoreboard? These four will be connected into the top module as the environment. Okay. For this top module is the test. For this top module is the test bench which connects the DUT and the test bench. Okay. So see environment class here. Here in this environment we have included all these because the environment is the top module, right? So we have included transaction class and generator, just the file name, generator file, driver file, receiver file, and scoreboard file, and transaction file. All these files are included here. Okay. And class environment we have created. For generator, we have created the G instance. For driver, we have created D instance. For receiver, we have created R instance. For scoreboard, we have created S instance. Why all this we are creating? Because in driver, see, in the generator, we have written many tasks and functions. In the driver, we have written many tasks and functions. Receiver, we have written many tasks and functions. Scoreboard also, we have written many tasks and functions. We need to access all those functions from this environment. How can we access all those functions? Through the object. That object is nothing but this instance, right? You got the point now? So we have created generator G, driver D, receiver or SBS. So these are the objects. And mailbox G2D and mailbox R2. Yes. If you see here, virtual interface, function new virtual interface, we have taken mailbox, two mailboxes we have taken because two mailboxes are useful in the environment, right? So this by using this, we have created the environment. And task build. What is the task build here? See in the here, what is this generator, right? Okay. Task build dollar display g equal to new of g2d. What is that new of g2d? In the generator we have created this constructor 10th line. If you see 10th line, function new of mailbox g2d. How you will access that mailbox g2d function is nothing but from the environment we are passing this value, passing that argument. 25th line, right? Like the d is equal to new of v FIFO dot g2d. This v function, where it is v function? Here in 7th line. What are the arguments in that new function? Virtual FIFO and mailbox. We are transmitting two arguments to that function. Okay, like that or equal to new function. Again in mailbox also we will have the two arguments in the function, right? See here, function new virtual FIFO mailbox. Okay. and scoreboard also same. And d dot d g2d equal to g2d. Okay, driver, for the driver, we are taking g2d mailbox. And for generator, g2d mailbox equal to g2d. R dot R2S, that means we are accessing all mailboxes here. Okay, mailbox. Okay. And task here, build a task completed. Okay, build a task is written in the environment. Okay, and task test, what is there in the task test? We are calling all the tasks. See here, d main or start s dot run. D main is nothing but, in the here we have the main task. This task is calling from the environment. In the receiver we have the task start task. The task is calling from the environment. In the scoreboard also we have run task. This task is calling from the environment. Okay, so those all. Join any g main task, g dot main task also you can call. Okay, and task post test. What is that post test? We are just telling that whether it is a passing or fail. Okay, so if g dot count is equal to d dot count, that means how many number of transactions. If we send 10 number of transactions, means those 10 from the generator side and the driver side must be equal. Okay, so begin d dot reset, display resetting past, otherwise failed at particular time. Okay, so this is the end task and end class. Okay, clear everyone up to here? Just environment is nothing but we are calling all the task and functions in the from the environment. Okay, whatever we have written in the environment, these post test task and build task, from where we will call those tasks? From some particular point. If you call only, it will come to this task, and again it will this functionality will be operated, right? So from where you will you will call this task? What is the top module for the environment?
Test, ma'am.
Test. From the test we will call the all task from the environment. Okay, see here, test, we have included tick include environment and program. Okay, only for the test we will write the program. Okay, program mostly it will create some race around conditions. So in the test only we will write with the program which eliminates the race around conditions. Okay, the race condition between the test bench and the design. Okay, so program test FIFO I in F. Okay, FIFO I is the interface name. In F is the name of the instance of the FIFO. Next, we have created 2 mailboxes and 3 transaction class, and environment E. Environment E is main here because object we need to create for the environment, and we need to call those tasks through the object, right? So see here, all the things we have created here, transaction and mailboxes, and initial begin if test dollar plus arguments t1. This t1 is nothing but displaying some value, some name. T1 is the name, and e equal to new int f g to d or to s. What is that? Here we have written function new, right? Though these arguments we are sending from the test. Okay, e dot build method. In environment we have the build method, build task here, right? So the task is calling from the from here. E dot count equal to 8. What is the count we are giving? E dot g dot count. See, observe here, e dot g dot count. E is the environment. In the environment we have taken g. From the g we are accessing the count value here, this count. Okay, so e dot g dot count equal to 8. Okay, can you join for the next session quickly? Okay, see here, e dot g dot main count value we have taken. uh, where we have taken e dot g dot count value we have taken. E dot d dot reset calling, we are calling the reset function, and fork join e dot g dot main, whatever in the generator we have, the main task. This is the main task, right? So how we are calling this main task from the test? E dot, first we are going to the environment. From the environment we are accessing the G. From the G we are taking the main, we are calling the main. And E dot test, we are calling the test in the environment. See here, this is the test, task test. And this is the if test, this is the T1. And test T1, T2, sorry, T2. And again E equal to, we are passing the arguments. Again we are taking the count value, new count value. And same, we are calling all the task. From here, join any, again we are calling the run task of generator. And the E dot test and reset task. Here all things are calling the task. Okay, all things are calling the task. Here dollar test, dollar plus args is there, right? I also don't had that idea. I'll tell you later. I just write long back I have written this one. I don't had that idea, so I'll tell you later. So this is how test, top test. And next, testbench.sv, actual test bench. Okay, see, actual test bench, what is there? We are including the test and the interface, module tb, clock reset, generator, driver, monitor, receiver, all the things. Okay, FIFO I test, this is the main DUT, interfacing the test bench with the DUT, same as a Verilog, how we will write, same. Okay, and initial reset equal to 1, initially after 10 time units reset equal to 0. And generating the clock. And dollar dump file and dump files is used to open the waveform. Okay, so this is the how we will write the system verilog test bench architecture. Okay, for every program we will follow like this only. Okay, same like this only according to your functionality and variables. The small difference is scoreboard logic. Scoreboard logic will be changed for all. Okay, so I'm running the program now. You can try with the different examples. Take a small example like a flip flop, or you can generate for the combinational logic circuit. Okay, so this is up to now system verilog has completed. Okay, so from tomorrow onwards we will see the system verilog projects. Okay, today time date is 6th, right? So from I will try to complete by 10th. System verilog projects will complete by 10th, and from 11th we'll start UVM. Okay, so everyone be thorough with system verilog concepts. Already I have given so much time. Okay, so much time I have given, but I don't know whether you utilize the time or not. So from 10th onwards we are going to start the UVM. Okay, try to clear your concepts before only. So if you see what is the clock, we have generated the clock. And d input, 8-bit input we have created here. And data output empty. Empty means initially empty is high, then empty is low. Okay, empty is low means it is not the data is not there, so we have taken inputs here. And full, if input, all the inputs are given, automatically the memory will get full, right? So here full is high. Whenever full is high only we can read the data, right? So if you see the counter value 0 to 8, initially we have taken 0 to 8. So here also 7 down to 0. And read data. So initially read is 0, that means write operation. Again read is 1, that is read operation. When we are doing the write operation, data input is generated. Whenever read is high, read operation. See here, read operation, suppose here 98, so 90, wait, see 98, 98, d5, d5, 06, 06, fb, fb, 2e, 2e, f5, f5, b5, b5, 4c, 4c. Okay, so first in, first out. Okay, this is how we have generated the input data and output data. Okay, these are the right pointer. See where right pointer is high, here, and this is the read pointer. Read pointer is high initially, uh, that means it is showing to the right data. Here right pointer should high, at this point it should high. We'll check why it is not high there. Okay, so did you understood the FIFO, everyone? And also you can check here also. We have written some monitor statements, dollar display statements, right? These all the things you can check here. What is the write enable? What is the data out? What is the data input? What is the full? What is the empty? Right? Generate a number of transactions. You can check all these things here. Okay. I will share you the code, and you can also try the code yourself and you can check. Okay, have any doubt anyone? System verilog, how to write the program using test bench architecture? Have any doubt? Have any doubt? I have shared the assignments for up to oops and randomization, right? Please try to complete up to randomization, and today I will share for coverage also. Okay, so have any doubts? Everyone clear? Okay, thanks. Okay, thanks. Practice well.
Okay.